So, yeah. So it's our pleasure to invite Joshua again to give his second talk on characterization by symmetries and P versus NP in GCT. Yeah, Josh.
Yeah. Thank you very much for inviting me for this second talk. Today what I want to do is sort of finish, well, not finish, but continue a little bit the story that we talked about last time about partially stable points. And that will lead us into a discussion of sort of the importance of symmetry groups for understanding these kinds of questions. And then I also want to talk about, rather than permanent versus determinant, how you actually could potentially get at P versus NP in GCT. And so again, most of the material, I mean, I'll give specific references as I state results, but sort of most of the big ideas here are from the original paper GCT1, and then, you know, some of them are sort of some things that have developed since. But okay, but I actually want to start today's story in a slightly different place, which is with what are called natural proofs. So this goes back to Razborov and Rudich. And the idea here was that, you know, people at the time, so this was like early 90s, had started to look at circuit lower bounds. So rather than just P versus NP, people were looking at NP versus what's called P poly. So this is sort of a non-uniform version of P, whereby non-uniform, what I mean is a Turing machine is sort of uniform in the sense of there's one machine for all possible inputs. And here, what we now have is we have a different machine for each input size, but you still want those machines to run in polynomial time. Okay. Or if you talk about them as circuits, as computer scientists often do, that they should have polynomial size. Okay. And part of the reason that people were doing this, like this seems like a harder problem. P poly is a much more powerful model than P. So why would you try and show NP was different from P by instead showing NP was different from P poly? Well, I mean, there are many reasons, but I think part of it is that circuits are somehow much more, it's a combinatorial object. It's, you know, it's a directed acyclic graph with gates at the vertices. And so you can sort of start to reason about how information is flowing through it. Whereas Turing machines are these very unwieldy things, and they have tapes, and they can write on the tape, and the tape can be arbitrarily large. And so they had started to develop some of these circuit techniques, and there were some exciting results at the time. You know, they had lower bounds on bounded depth circuits. Razborov famously had lower bounds on monotone circuits, which is circuits which don't use negations. And what Razborov and Rudich said was essentially all of the circuit techniques that they knew at the time satisfied some properties. And so they called any proof satisfying these properties a natural proof, which, you know, natural is one of these very overloaded words. But anyways, the name stuck. What they said was basically, if there is a natural proof, where here, this is now a technical term of art, there's a real definition here, and I will give you the flavor of this definition. I don't want to get too much into the details, but I'll give you the flavor. So if there is a natural proof that NP is not in P poly, then essentially sub-exponentially hard pseudo-random generators do not exist. Okay, if you don't know what a pseudo-random generator is, that's okay. maybe the one thing I'll say about this is, for example, most pseudorandom generators based on factoring, based on our current state of knowledge, are at least this hard. So in particular, if there's a natural proof that NP is different from P poly, then all pseudorandom generators based on factoring, based on what we currently believe is the hardness of factoring integers, can be broken. Okay. So this violates a pretty natural and widely held assumption. And so this was sort of taken as evidence that there do not exist natural proofs that NP was different from P poly. Okay, and so let me just give you the flavor of what it means. Okay, and rather than focus on the proof, what they actually said was most lower bounds focus on a property. And so really what they said was, they gave a definition of a natural property, and they said if there's a natural property that separates NP from P poly, then sub-exponentially hard pseudorandom generators don't exist. So a natural property of Boolean functions okay, and I will only sort of define this for you, is a subset Cn of Boolean functions on n variables. So let me just say functions from 0, 1 to the n to 0, 1. That is large, meaning it contains a large fraction of all functions. It is constructive, meaning given the truth table of Fn, can decide whether Fn has this property in, well, polynomial time in the size of the truth table, which is 2 to the n, because it's an n-bit function. Okay, and it should be useful against P poly. So useful against P poly in the sense that if you have a sequence of functions where Fn is in Cn, then this family is not in P poly. So if you have a sequence of functions that have this property that is large and constructive, then those are not in P poly. So the idea is a natural proof that NP is not in P poly is really a natural property. So it's a subset of Boolean functions that's large, constructive, and useful against P poly, where you can show that there's some language in NP that has this property. So this is very much in line with sort of what we've been talking about the whole time of you find a property that separates your hard function from your easy class. But somehow all the known techniques at the time and still essentially today for non-uniform lower bounds, they have these additional features. Okay. And this was one of the things in sort of any serious attempt at P versus NP that you have to get around. And so in GCT1, they actually spend a fair amount of time discussing, okay, how is the GCT approach going to get around this? And okay, the message here is you have to violate one of these 3 things. Okay, you can't violate this because this basically says this lets you prove the lower bound. Okay, so you have to violate really one of these. And there's actually some evidence, Ryan Williams has some nice papers that says you almost can't get away with violating this. Although that paper didn't come till much later, I think people kind of had that feeling that like the reason that these properties should be constructive is because we humans came up with them. So like it's a property that we can reason about, and it feels unnatural or unlikely that you would come up with a property that you can reason about so well that you could use it to prove lower bounds, and yet that property would be so hard that you can't decide that property in 2 to the n time, 2 to the O of n time. So the real thing to violate was this one. So, okay, the message, and I should say this is my view. There are other people who share this view. This view is not universally accepted, but it's part of our story. So the message here was a lower bound technique. It really shouldn't apply directly to random functions. Or flipped on its head, what we say is a lower bound technique should really leverage something special about the function it is proving a lower bound on. So this is like the hard function, set, permanent, and so on. Okay. All right. So with this background in mind, as sort of our backdrop, I now want to come back to stability and partial stability. Okay, so last time we talked about what is the definition of partially stable, and we did some examples, namely, matrices of low rank under the action of left and right multiplication, and also things like the padded permanent, where you've embedded the permanent into the space on many more variables, and that was like the key example in GCT1. Okay, but what we didn't talk about is, what do these things get you? Why are these things nice? Okay, so stability implies a number of things that are nice. Okay, and some of these things I will say more precisely, and some of them I will say less precisely to sort of tell that part of the story, but there's too much background to go into it in detail. So one thing is Luna's étale slice theorem. So what this tells us in this context, and what is our context here? So we have a point X in some vector space V. We have our big group G acting on V. Okay, and throughout, just for simplicity, I'm going to let H be the stabilizer of X. So this will play an important role. And if I had to write and say stabilizer every time, it would become very slow. So, okay, what does Luna's étale slice theorem say? What it says is a neighborhood of the orbit Gx is, let's say, almost isomorphic to G cross Hn, where this is like a normal vector space where it's normal to the orbit. So I'll draw a picture in a second. Okay, and what this notation is telling you is it's sort of looking at pairs of normal vectors and group elements, but where you can sort of pull the H through. So if I had an H here, so it's looking at pairs like this, but where in this space, this is equivalent to H acting on this normal vector. Okay. The picture to have in mind here, I think, is if you imagine your orbit as a line, that there's some neighborhood of the orbit where what you see is basically these vector spaces So these are all copies of n, our normal space, sort of smoothly varying along the orbit. And then what happens is, so there's a neighborhood that looks like this, and that means that nearby orbits also kind of have this same shape. They sort of go through n in the same way. Okay. One thing that this implies, and this is going to be key for our story. Oops. So one thing that this implies is that if there is a point y in the infinitesimal neighborhood of gx, then the stabilizer of y is essentially contained in the stabilizer of x, where really there's some conjugate of this that's in the stabilizer of x. So maybe let me actually, rather than say that, let me say this. If there's a point y in the infinitesimal neighborhood of x, then there is a y prime in the orbit of y, such that the stabilizer of y prime is actually contained in the stabilizer of x. Okay, so the example to have in mind here is where x is the permanent, or if you like, the padded permanent, depending on what setting you're in. And maybe let's say the padded permanent, actually. And y is, say, the determinant. Okay, so if the padded permanent were actually stable, then what this would say is that the stabilizer of the determinant, some conjugate of the stabilizer of the determinant, is contained in the stabilizer of the permanent. So if you wanted to prove that this didn't happen, which would separate our class varieties the way we want, it's enough to literally just look at the stabilizer groups. Okay. Now, the permanent itself, if you do no padding, this is actually fine. So the stabilizer of the n by n permanent, it's essentially, you have a bunch of scalars. So 2n minus 1. You can multiply the rows by whatever you want and the columns by whatever you want, as long as the product of all those things that you multiply by is 1. And then you can also permute the rows, permute the columns, and you can take transpose. Transpose. This is permute rows. This is permute columns. And this is scale rows and columns. Okay. And the stabilizer of the determinant is essentially I'll write it like this: S GLN cross GLN semi-direct S2. So again, this is transpose. Okay, and what does this notation mean? By this notation, what I mean is the set of pairs AB where the determinant of their product is 1. So this is, you can left and right multiply, right? So what's happening here is det AXB equals det X, right? As long as the determinant of A times the determinant of B is 1. So it turns out that both of these points in the natural space in which they live, so in these are degree n homogeneous polynomials in n squared variables, these points are both stable. Actually stable, not just partially stable, actually stable. Okay. So one consequence of this thing is we can prove that the permanent and the determinant are not in the same orbit here. They're not even, in fact, the permanent is not even close to the determinant. So proving they're not in the same orbit is easy by looking at these stabilizers, because to be in the same orbit, their stabilizers would have to be conjugate. Right? Okay, so one, perm and det not equivalent to one another, not in the same orbit. Okay. And why am I telling you this? I mean, we kind of knew this, but I'm telling you this because the point is we can tell this entire story just in terms of their stabilizer groups. Okay, and the reason is if y is in the orbit of x, say y equals gx, then the stabilizer of y is, well, basically what you do, you undo g, so now you have x, you do the stabilizer of x, and then you redo g. So the stabilizers would have to be conjugate, and in particular, they'd have to be isomorphic. Okay, but these two groups are not isomorphic. You can see that in a wide variety of ways. One way you can see that is by dimension, that this part is finite, so this group has dimension 2n minus 1. This part is finite, this group has dimension 2n squared minus 1. Okay, so perm and det not equivalent. Why? Their stabilizers aren't isomorphic. Maybe I should say aren't even isomorphic. I mean, they could have been isomorphic but not conjugate, but they're not even isomorphic. Okay, but the second thing is that what we get from stability from Luna's étale slice theorem is that the determinant is not even in a nearby orbit. Or maybe more precisely, that there's a neighborhood of the permanent orbit that does not contain the determinant. Okay, and why? Well, let's go back. So what's the interesting consequence that I want to focus on here is, if it were, then the stabilizer of the determinant would have to be contained in the stabilizer of the permanent, or some conjugate of it would. So if it were, proof. Oh, and I should say, okay, now we're into the territory where maybe we're starting to be a little less background, and this kind of thing, it's I don't think it's stated as a theorem in GCT1, but it's certainly discussed in GCT1, where there, again, basically has background to this notion of partial stability. Okay, so determinant not even in a nearby orbit of the permanent. If it were, then the stabilizer of the determinant would have to be conjugate to a subgroup of the stabilizer of permanent. But now we can argue just by dimension. So we said the dimension of the stabilizer of the determinant was essentially 2n squared minus 1, which is much bigger than the dimension of the stabilizer of permanent, which was 2n minus 1. Okay, so we're starting to now, okay, this was not maybe super interesting because it was like n by n determinant versus n by n permanent, whereas we want to talk about, in the end, we want to talk about like an exponential gap between the determinant and permanent we're talking about. But like, I find it very interesting that even in this sort of base case where they're the same, that you can reason entirely about the stabilizers to talk about this thing. Okay. All right, so this is a thing we're going to come back to. One other thing I want to mention about stability. So stability also implies, and here I'm just going to say some words that are really more for the experts, but we'll see that the story is like, it implies something very nice. Partial stability implies something less nice. So stability also implies that higher cohomology vanishes. And okay, not exactly, but sort of morally, what this tells us is all of the information that you want is in the coordinate ring. And maybe I should say sort of all relevant, I don't know, topological information is in the coordinate ring. Now, phrased this way, it may seem a bit strange because, you know, from the background lectures on algebraic geometry, in some sense, all the information is in the coordinate ring. The coordinate ring defines the variety. In some sense, what this is telling us is, okay, cohomology is some topological tool for understanding spaces. And what this is telling us is that that tool here is only useful in sort of its base case, that the higher cases don't give you new information. Okay. All right, so then the question is, stability was very nice, but in GCT, because of this issue of you're embedding a function on a small number of variables into a space on many more variables, you only get partial stability for those functions. And so the question is then, what do you get that's sort of an analog of these things from partial stability? Oh, right, I guess I should say there are some other nice implications. So also nice implications for the representation theory. And these, both for stability and partial stability, these are explored and developed much further in the paper GCT2. Okay. All right, so right, what does partial stability get us? So partial stability, it doesn't, of course, quite get us everything that stability gets us, but it does give us some nice things. And one that I want to highlight is this sort of weakening of Luna's étale slice theorem. And so this is, right, okay, so this is now GCT1. Okay, so partial stability implies, so if X partially stable, then what we get is that the orbit itself is now a fiber bundle over a Grassmannian with affine fibers. Okay, so this is G mod P, and these affine fibers will be L mod L prime. So if you go back and you look at the definition of partial stability from the previous lecture, this is how sort of the notation lines up. What this is telling you is that the orbit looks like, for every d-dimensional subspace, so that's what the Grassmannian is characterizing, you can pick a vector in here, and you get some point in the orbit, and that association between d-dimensional subspaces and vector and points in the orbit sort of varies continuously as you change your d-dimensional subspace. Okay, so this gives some nice structure to this orbit, and in particular, so if you want the precise reference, it's theorem 5.4 in GCT1. Tells you that, so the cohomology no longer vanishes, but that the cohomology of the orbit, cohomology of Gx, is, let's say, essentially the same as that of the Grassmannian. Okay, and the latter, this is like a well-studied thing. Okay, so this is one thing that partial stability gets you. And then there are also further representation theoretic things that it gets you that are discussed in GCT2. Okay.
Sorry, I have just one question, Josh.
Yeah.
So when you say, okay, so is it that it's not true that when it is stable, the orbit is normal, right? The orbit is closed, but the coordinate ring need not be normal, no? Or is it?
Oh, I see. So, sorry,
or you're looking.
So the orbit itself is always smooth. So it's normal, right? The orbit closure, no. I mean, I don't think. Oh, sorry. When it's stable, the orbit is stable. It is closed. So then it's fine.
Okay.
Right.
Okay.
Right. Yeah. No. Certainly. I mean, we know. Shravan Kumar proved.
Yeah. Correct.
I don't know, 10 years ago or something, that these determinate and permanent orbit closures are not normal.
Yes, but that is of course all in projective space, right? We have to do it in.
Oh, yes. Okay, I don't know, but I don't think you get anything as nice as normality.
Yes, you don't.
Just
yeah,
from looking at
far from the normal. Yeah.
I think even in the partially stable setting, things can be very far from normal. Yes. I think.
Yeah. Thanks.
Okay, so part of the reason I wanted to highlight this is I think this is an area sort of ripe for further study, in the sense of, okay, first of all, partial stability itself as a notion, but in particular, these higher cohomology groups. What this is telling us, and what they propose in GCT1, is that actually in the setting of partially stable points, which is what we have, that you use not only the coordinate ring to get obstructions, but that you somehow also use the higher cohomology groups. And so understanding these cohomology groups, and in particular the relevant representation theory on acting on the cohomology groups and how that's related to all the other stuff we've been talking about, that strikes me as a very interesting area for deeper study. Okay, so now I want to come back to this story about stabilizers. Okay, because, so one of the things was, okay, in the stable case, right, you know a lot about the orbit and its neighborhood. And in the partially stable case, we also have this very nice structure to the orbit. Again, Christian in his first lecture mentioned, okay, you can look at multiplicities in the coordinate ring of the orbit, not the orbit closure, but the orbit. And that those came from, all right, so this is maybe now like a little bit of a break. So coordinate ring. Maybe I should say ring of regular functions rather than coordinate ring. So ring of regular functions on the orbit Gx. Okay, so I guess I might denote it like this, but this is not to imply that GX is an affine variety. It need not be Zariski closed. We just want to consider regular functions. So, going back to one of the earlier algebraic geometry lectures, these are functions which look like ratios of two polynomials locally, where the denominator doesn't vanish. So as you move around the orbit, in principle, you could have different denominators for the same function. Okay. All right. And what this is, Christian told us in the first lecture, this is, you take the coordinate ring of the group and you look at the things that are invariant in this coordinate ring under the stabilizer. Okay, and so here, and then from here, you can say, okay, if I want to understand, say, the representations arising here, you look at the representations here and you see what happens when you restrict them to the stabilizer. So here again, we see the stabilizer showing up as sort of in an important role. And I wanted to take a minute to just give you a feel for like why this is true. Okay, and here, okay, if you know the relevant algebraic geometry, I think everything I'm going to say is sort of fine from the algebraic geometry perspective. But you can also just think about this in terms of groups. Like imagine these are, I don't know, I don't even know if I need things to be continuous. So you have a group G, remember H will be our stabilizer. And the orbit stabilizer theorem in group theory says that as G sets, meaning sets with an action of G, the orbit is isomorphic to G mod H, the coset space. Okay, so if I want a function on the orbit, one thing I can ask is, well, what do I need to require of a function on G so that it gives me a well-defined function on the orbit? So what do we need to require of a regular, I guess? But actually at this level, I don't need regular. When you move to the AG level, you need to say regular, but let's just say, what do we need to require of a function, any function, on G to have it give a well-defined function on G mod H? And one thing is, well, okay, if I have a function on G, so, okay, imagine I'm at a point, little g, and I have my function value, f of g. Okay. And I imagine sort of wandering around G, okay, and as I do that, my function varies, right? As I look at different points in G, my function takes different values. And then say I come back. Well, I better be back to the same function value. Okay, but in G mod H, coming back includes landing in the same coset as G. So now what I want to say is, even if I land at GH, or some H in H, the value better be the same, because I need it to be well defined on these cosets. Okay, but this is precisely saying that F is H invariant. Okay, all right, so that's where this little bit came from, and this is why it's easier to get a handle on the representation theory of the orbits than their closures, because the Peter-Weil theorem tells us what this is. It's essentially a sum over all irreps of G, with each one appearing with multiplicity equal to its dimension. And then it's just a question of restricting those irreps to the stabilizer. All right, so again, we see stabilizer playing sort of a very important role here. All right, and one issue, if you were to take sort of an arbitrary function, even an arbitrary function in VP, for example, or in VNP. So most functions, most, let's say, polynomials, have trivial stabilizer. Okay, so the first thing is having a non-trivial stabilizer at all is already a special property. Okay, and so morally, if you're using something about the stabilizer in your lower bound proof, like that could be enough to get you around this natural proofs barrier. Okay. Now that's still very, I don't know, hand wavy, right? In that, I mean, okay, yes, I haven't told you definitions, but even if I told you all the definitions, that last statement would still be somewhat hand wavy. In GCT1, they sort of propose much more specific ways in which to leverage the stabilizer. Okay, and this brings us to characterization by symmetries. Where let me start with examples. So what do we mean when we say a function is characterized by its symmetries? Well, there are a variety of things we could mean. And actually, I would say it's not 100% clear yet which of these we want in all cases. But let me say sort of the cleanest version. And here it doesn't actually have to be functions. You can talk about any point in any G module. So let's say V is a representation of some group G, and we have little v in V. Okay. So one definition is V is characterized by its symmetries if any other point, or maybe I should say there are no other points with the same symmetries as V. So if, so for all V prime, if G stabilizes V, then G stabilizes V prime. If this is true, then V prime is a scalar multiple of V. Okay. You can't do much better than scalar multiples because scalar multiples will always commute with the action of your group because it's scalar multiples of the identity matrix acting. And so the scalar multiples of a vector always have the same symmetries. Okay. So this is saying it's sort of as characterized as it can be. An equivalent way to say this, equivalently, we would say if the stabilizer of V prime contains the stabilizer of V, then V prime equals lambda V. And in this case, this implies that actually these stabilizers had to be equal. Okay. So morally, what such points are is if I've told you they're stabilizer, I've told you everything. Okay. And that's very nice because all these things we were talking about up here, these were all in terms of the stabilizer. So we would like to know that when we're talking about the stabilizer, that that's sort of without loss of generality, that you haven't lost too much information by focusing so much on the stabilizer. And in some sense, that's what you get from characterization of symmetries. Okay, now part of the reason this notion examples of this go back far. like to Frobenius in the 1890s. Okay. The notion itself and its importance and this definition, these things really, as far as I know, really came out of GCT1. Okay. So the key examples for us will be determinant, permanent, and iterated matrix multiplication, and several other polynomials of complexity theoretic interest. Okay. And so this example of the determinant, it really goes back to, as I said, Frobenius. But you know, he didn't have this definition, so he didn't just say, "Oh, the determinant is characterized by its symmetries," but you know, he wrote down the theorem. Okay, and let's see, how am I doing time-wise? Great. Let me just see.
45 minutes more, around 45 minutes more.
Yeah, perfect.
Halfway through.
Okay. All right, so I want to talk a little bit about characterization by symmetries, and give you some feel for it, and then finally come back to talk about P versus NP in the context of GCT. Okay, so let's actually do, we can actually do characterization by symmetries of the determinant. So theorem, like I said, this goes back to Frobenius, 97. That's 1897. Det is characterized by its symmetries. Okay, and this proof I find particularly interesting. So not all of the proofs of characterization by symmetries go this way, but one way you can prove this is by Gaussian elimination, that there's some very close relationship between the fact that you can compute the determinant efficiently and the fact that it's characterized by its symmetries. So first, just to recall, stabilizer, like what symmetries do we have here? So stabilizer of determinant essentially comes from the fact that det AXB equals det X when det AB is 1. Now, one thing that might be a little confusing here in this notion of characterization by symmetries, note there's also a determinant here. That determinant is like separate. This is like in the definition of the group. These ones are the function we're talking about. So now what we want to say is, suppose f is a degree n homogeneous, f of x is a degree n homogeneous polynomial in n squared variables. So, right, it's in the same vector space that we're living in, such that f of AXB equals f of x when, and now it's still det here, det AB is 1. Okay, because again, this one is in the definition of the stabilizer, like we're using this as a shorthand to describe what the stabilizer group is. It's you know, coincidence, sort of miracle of linear algebra kind of thing, that the function we're talking about also shows up in that description. But in terms of characterization by symmetries, this is the thing we want. So this is still just our shorthand for describing the group, but this is what we want. So we don't want like f of AB equals 1 here. Now, a consequence of the theorem is you could have equally said f of AB equals 1, but that's not the definition. Okay, so the point is, if f has these, you can start using A and B to do Gaussian elimination on X. Right? So what are the steps of Gaussian elimination? So I'm not going to go through the whole thing, but Gaussian elimination involves, so scaling rows, adding one row to another, and I guess sometimes permuting rows. Okay, but all of these things can be achieved using invertible, in fact, invertible A here. Okay. And what do you get at the end? At the end, okay, and then using B, you can actually make your matrix diagonal. Okay, and at the end you have a diagonal matrix, and so now you just have to deal with F on diagonal matrices versus determinant on diagonal matrices, and now it's easy. Okay, so okay, this was not a proof, but this was like a proof sketch. Okay. All right. By the way, one interesting question. So not only is having a non-trivial symmetry group already a rare property, so if you're using a symmetry group somehow non-trivially, you're potentially avoiding natural proofs, but being characterized by your symmetries is even more rare. Okay. Right, one interesting question here is, here I'm being a little bit hand wavy. In Razvarov-Rudich is really about Boolean functions. And here we're talking about algebraic complexity. And so there was a question for a long time of, is there an algebraic analog of the natural proofs barrier? Scott Aronson and Andy Drucker had a nice proposal that then Mrinal Kumar, Mike Sachs, Shubhangi Saraf followed up on, and independently Ford, Spielke, and Volk. I think this was also mentioned by Christian, who's done some follow-up work on it. So there's a whole theory there, but that's a different talk. That's a whole separate thing now. But the thing I want to mention is, okay, if we go back to Razvarov and Rudich, even philosophically, one of the things that they said was constructivity, about, how easy is it to decide this property? And so I think it's an interesting open question. If I gave you a polynomial, and okay, what's the analog of a truth table for polynomials? It's like listing out the coefficients of every monomial. How hard is it to tell if it's characterized by its symmetries? So how constructive is this property? So given a polynomial f, say by its list of monomial coefficients, how hard to tell if it is characterized by its symmetries? Okay. And one thing I'll mention here is, okay, in the case of the determinant, it's actually not too hard, because it's not only characterized by its symmetries, but it's characterized by its continuous symmetries, by the identity component of its stabilizer. You don't need the finite part. You don't need the transpose, right? Like in this proof, when you do your proof by Gaussian elimination, you never need to use transpose. Transpose actually comes for free, which is kind of interesting, right? If you have a polynomial with these symmetries, it is automatically also has transpose as a symmetry, right? That's kind of interesting. Okay, but the permanent, you really need the finite part, the fact that you can permute the rows and permute the columns. You don't need transpose for permanent characterization by symmetries either, but you do need to be able to permute the rows and the columns. And actually, it's that finite part that makes this question interesting and difficult. that the identity component, the continuous part, you can do basically using, you can answer this question essentially using linear algebra by looking at the Lie algebra. Okay. So the interesting hard part here is the finite components.
So in, I just want to ask, so in this question, is F presented to you as a circuit or something? Are we thinking of that?
Oh, no, right. So here I'm saying, suppose it's presented to you by, I give you the list of all its coefficients.
Okay. Of all,
right.
Okay.
Right. It's also an interesting question to ask. So why this? Well, this is sort of the analog of Rasburov-Rudich saying you're given the whole truth table of a Boolean function.
Okay.
It also strikes me as an interesting question. Say F is given to you by a circuit or as a black box that you can evaluate. You can ask the same question. And that also strikes me as interesting, but this was just for sort of the analogy with Rasburov-Rudich.
Oh, okay.
Yeah.
And implicit in this, do we already know that we can decide this and we just are wondering if we can do it efficiently?
Oh, yeah, it is surely decidable. Okay, I should be a little careful. If you're over an algebraically closed field, it is surely decidable because you can write it down as a first order statement with a couple of quantifiers, and so you can do quantifier elimination. So like, yeah, decidability is not the issue, efficiency is the issue.
Okay, thanks.
Okay. Let's see. I think maybe I will skip that. Yeah, okay. So I want to get to P versus NP in GCT. Let's see. Sorry, I'm reordering things on the fly here. Yeah, okay. All right, so now we're in this setting where, okay, the symmetry group seems to be very important. It gives us a lot of information, right? It gives us information both representation theoretically and geometrically. And so we would like points that are both symmetry characterized and at least partially stable. Right? And these are like the kinds of assumptions that they make in GCT2 to get all sorts of nice representation theoretic consequences. Okay, but now I want to talk about, okay, so we want points that are characterized by their symmetries and stable or partially stable. How do we get at P versus NP? So, you know, when we talk about determinant versus permanent, the story is kind of like this. So the determinant can be computed in P, which is contained in NP, which reduces to the permanent. But the permanent we actually think is much harder than NP. So NP is about deciding existence of, I don't know, combinatorial witnesses. You know, does there exist a satisfying assignment? Does there exist a Hamiltonian path? Does there exist a clique? Permanent is about counting them. So how many satisfying assignments are there? How many cliques of size k are there? And so on. And Toda's theorem tells us that that's at least as hard as the whole polynomial hierarchy. And so we think permanent is actually much harder than NP. And so the question is, how do we really get at these things? And I guess it's not quite P, it's really, I lied a little bit, it's really like P poly, right? Because everything we do will be non-uniform. Okay. So instead, in GCT1, they propose two different polynomials to look at, which are much closer to P versus NP. And then we'll talk about how do we get to actual P versus NP. Okay. So And these polynomials, I'll stick with their notation. So there's a polynomial h, which is p complete. Okay. And then there's a polynomial e. E actually, we'll get there. It's not known to be NP complete, but there are good reasons to think that it's hard. So it's in NP and we think it's not in P. Okay, so what is this H? H is like a generic circuit. So what it looks like is you have some inputs, x1, x2, xn, and you have a layered circuit. Okay, and right, and then what happens is every node here is actually connected to all nodes here, but with some weights. And so when I have a node, let me choose my notation carefully. If I have a node here, u, let's say at node u, the function little h of u will be the sum over y u v w h of v h of w. So this will be the sum of vw in previous layer. Okay, where at the bottom layer, right, h of this node is just x1. So h of xi is xi. Okay, so our variables here in this h, okay, and then at the end, there's one output, okay, which has the same form. So the final layer has one thing. Okay, this final output, so we call this out. So h of out, if you sort of unravel all of these things, it's a polynomial in the x's and the y's. So you can think of these y's as sort of weights in between the layers. So h out is a polynomial in x's and y's. Okay, and this is our h. Why is this called a generic circuit? Well, the idea is if you wanted any poly-size circuit, you just specialize these y values to be the weights that you need so that this looks like the circuit you were trying to simulate. So that's what I mean when I say this is sort of P complete or VP complete. So, okay. And over a finite field, you know, this really captures P poly. So H over a finite field is really equivalent in power to P poly. And here, this equivalence is now really formal, that if something can be computed by poly-size Boolean circuits, then it can be computed by poly-size projections of H over a finite field and vice versa. So here now, like, you know, because we've moved to a finite field, we're now legitimately talking about a Boolean complexity class here. Okay. It still has a very algebraic feel to it, but it's really a Boolean complexity class now. Okay, and this is what we want. This is precisely what we want, right? We want an algebraic feel to a Boolean complexity class so that we can apply all of this algebra to reason about Boolean complexity classes. Okay, and then the function e, this is designed to capture NP. So, okay, E, E is a bit more interesting. So E is, you imagine that you have K matrices. So these will be K m by m matrices. Okay. And then given a function I will build a new matrix, X sigma. So this will be an M by M matrix whose ith column is the ith column of X sigma I. So I'm piecing together this matrix by choosing columns from these K matrices. Okay, and then E of X will be the product over all such sigma of the determinant of this. Okay, so this is the polynomial that they propose to capture NP. Now, in terms of sort of ordinary algebraic complexity, this polynomial seems bad because like there are exponentially many choices for sigma, so the degree here is exponential. Whereas in most of algebraic complexity theory, one restricts attention to the degree being bounded by a polynomial. But this has some properties that make it much closer to NP than the permanent. So right, so one thing is, let's see, for integer matrices, even with just k equals 2, so a pair of matrices, and you build up a matrix by picking columns from that pair in all possible ways, testing if this is 0 is actually NP complete. So this is a result of Gurvitz 05. Okay. Contrast this with the permanent. For permanent of integer matrices, testing if it's 0 seems to be much harder than that. Okay. Other things we can say, so for example, if you consider this over a finite field, which is ultimately where we want to be headed. Okay, over a finite field, when I raise things to the qth power, they become 0, 1 valued. Sorry, to the q minus 1th power. They become 0, 1 valued. Okay. And this function really now is in NP. Okay. Whereas over the permanent, again, we think that's really not true. That the permanent, even if you do this little trick, that it still is much harder than NP. That it's still as hard as the polynomial hierarchy. Okay. So evaluating this function. So okay, E of X itself, like it's not exactly in VNP just because its degree is too large, but evaluating it seems to be in P. Okay, and so E of X is characterized by its symmetries. H of Y is sort of almost characterized by its symmetries. So if you look at this function H, there are lots of symmetries you get by like permuting within the rows here. It's not quite characterized by its symmetries as far as we know, in that it seems like there could be other polynomials with similar combinatorial symmetries. I don't know, it feels as though this is in some sense the simplest polynomial with these symmetries. So this gets back to what I said before of, okay, there may be some cases where the definition of characterization by symmetries, as I said it above, doesn't quite apply, but sort of almost applies. This is one of them. Okay. E of X is really characterized by its symmetries, which is maybe not too surprising because of this determinant here. So there's something, sort of highly symmetric happening. Okay. All right. And because of this thing that evaluating it over a finite field is really NP complete, now, if you want to talk about P versus NP in this context, one thing you can say is consider any function that evaluates the same as E of X over a given finite field. Okay. And so we'll say, just for shorthand, we'll say two polys are FP equivalent if their evaluations at all FP inputs are okay. So there are two conjectures in GCT1. I guess maybe this is hyphenated. One is no function FP equivalent to E of X is in the orbit closure of H of Y. And actually, even more strongly, they conjecture that you can tell this from the stabilizer. So also stronger conjecture regarding the stabilizers. Okay, which I will leave to their paper. And they also conjecture same that any function FP equivalent, sorry, I should say any polynomial FP equivalent to E of X is partially stable. So the original stability of, sorry, and I should say even to, not just to E of X, but even to padded versions of E of X. Okay. So, okay, the fact that E of X is partially stable, that they prove, and padded E of X is partially stable. But here what they're conjecturing is that actually somehow that partial stability is not just because symbolically it's this big product of determinants and so they can prove partial stability, but that actually the fact that evaluating it results in what it does, that alone is enough to get partial stability. Okay. And if this conjecture is true, well, functions FP equivalent to E of X, like evaluating E of X at FP points is a question in NP. The orbit closure of H of Y over FP includes all of P poly. And so this conjecture literally implies NP is not in P poly. So, okay, this is one way to sort of massage your way from the algebraic world to the Boolean world while still saying sort of very algebraic things. Now, there are many difficulties along the way, right? One of which is functions FP equivalent to E of X. Like, okay, first you have to understand what those are. One of which is everything is harder over finite fields mathematically. I shouldn't say that, but let's say algebraic geometry is harder, representation theory is harder. So it's sort of everything you look at in GCT is harder over finite fields. So there are many things like to get to the point where one might even dream of proving this conjecture. There are many, many obstacles still. But the point is, at least you can make this statement that is really NP versus P poly, right? It's not, oh, here's an algebraic analog. It's kind of like, no, it's really NP versus P poly. Okay. And then the last thing I want to highlight, like one of the things that I find very interesting about this is, okay, permanent and determinate, very natural. But we now have some criteria for what you want in a polynomial to sort of think about applying GCT to it. So you want things like stability, and so you want stability and symmetry characterization. And so you can now start to think, you can go look at like other polynomials of complexity theoretic interest or other complexity classes and say, what polynomial could I use that has these properties? And you can start to think about those classes in a GCT way. And so one I just want to highlight is you can also do this for graph isomorphism. So this is now a different approach to graph isomorphism than I talked about last lecture. So there's a polynomial, which maybe I'll call GI of XY. And I'll write out what it is, and then I'll tell you something about it, and then that will be where we close. So this is just to sort of illustrate, there are lots of other things that you can think about, and you can think about developing in sort of this GCT framework. So, okay, it will be the sum over all permutations pi. So imagine these two are n by n matrices, right, which we're thinking of as adjacency matrices of graphs. Okay. Pi in Sn of the product. And let's think of these, rather than 0, 1 adjacency matrices, let's think of them as plus minus 1 adjacency matrices. Okay, so this will now be the product over I and j of xij plus plus y pi I pi j. And my claim is that if you have two graphs and you plug in their plus minus 1 adjacency matrices, that this ends up being 2 to the n squared times the number of isomorphisms, graph isomorphisms, x2. Okay, so this lets you count graph isomorphisms. And the interesting thing about graph isomorphism, there's a theorem that goes back to Mathon 79, which is that deciding graph isomorphism is actually polytime equivalent to counting the number of graph isomorphisms. So unlike the case of permanent, where counting seems to be much, much harder than deciding, for graph isomorphism, counting and deciding are the same. So if you have this polynomial that counts graph isomorphisms, the algebraic complexity of this polynomial is essentially, in some sense, the algebraic complexity of graph isomorphism. Or let's say an approach to the algebraic complexity of graph isomorphism. Okay. This polynomial, hopefully it's not too hard to see, it has a fairly large symmetry group. And like their polynomial h of y, this polynomial is not quite characterized by its symmetries, but there's a sense in which it is sort of the simplest polynomial with its symmetry group. Okay. And then one final question. Okay, so you know, the message here is right, we have these nice properties, so you can go think about sort of, okay, for your favorite complexity question, are there polynomials with these properties that capture that complexity question? Okay, and maybe that is a good point to stop. So I will stop there. Thank you.